Hello, my name is Adrian Medacco, and my final project topic is the physics of the eyeball related to lens. In order to demonstrate this, how the eyeball uses physics in order to perceive images, we're going to be using Snell's law. We'll be demonstrating this using a laser and a glass lens, and pointing the laser into the glass lens in order to show the refraction that the eyeball does when light enters the eyeball and refracts onto the retina in order to form. Here I've drawn a diagram of the eyeball. Image formation occurs on the retina, and the center of that image being the fovea. The cornea and lens form a system that allows for refraction. So this would be the cornea/lens area. When light hits the cornea and lens at any of these angles, we can tell that they wouldn't have the same trajectory. So this lens allows for refraction in order for the image to be perceived. So they're all hitting the center of the retina. And then that information is then translated to the optic nerve, which leads to the brain and allows us to process said images. Here, in order to demonstrate the physics of the eyeball related to the lens, we are using this prism, which acts as the cornea and lens that form the single thin layer that acts as the lens for the eyeball, right? So we can use this to demonstrate how with light, once light hits the eyeball, it has to hit it at an angle that it can, in order to form a clear image, it has to hit it at an angle in which it can hit the retina in order to form an image. So.
Okay, so now we want to show the creation of the refracted angles and how the light refracts once it reaches the retina, right? So here we'll have the ray of light hitting the lens in a straight line. And now from there we can see how it refracts and hits an angle, which is essentially how image formation works once it reaches it. So we want a straight line reaching this lens. So we'll use this as light ray number 1. So now we have this, and we'll shine the light directly around this path, on this path. And we will make reference points on the other side. So here we have now we just connect them from the point it leaves the lens. And now we'll repeat this at other angles in order to maintain that this is consistent. So we have a straight line, say here. Now we'll put the prism back, shine the light at this directly on this line, and now we'll create our reference points again. So we have one. Then we can connect these. And we'll try one on this side. We'll create our reference points for this one. And from there we can see that all the light rays connect sort of in this area. They should all connect in this area right here. And now all that's left is to determine our angles just by connecting these. Because what happens is once the light hits the lens, there's refraction creating this angle, and then as it leaves, it's refracted more, and then it follows the path to the retina. All right, so here I have my diagram with all my angles. Now I'm going to use Snell's law in order to determine the index of refraction of the lens, okay? So we're gonna use this as angle 1, and this will be the angle 2, because they both share the same normal line. So we'll do 1.0 sine of 17 equals N2 times the sine of 11. So we'll divide sine of 11, and we should get around 1.53. And that makes sense because in our demonstration we're using glass for the prism is made out of glass, and that's around the index of refraction of glass. So I'll repeat the same for this orange line, this orange ray of light. So we'll use 15, the sine of 13. So let's see. Whoops. That should give us and that's about 1.15 equals N2 for this one. That's a little lower, but that's to be expected when we have measuring discrepancies around here. And now finally we have our last angle. So we'll use 17 and 12. So we have sine of 12, 1.0 here. Now we divide out the sine of 12. This should be 17. Now we get 1.40, which is pretty close to the index of refraction of a normal piece of glass. So since these indexes of refraction are pretty close to each other, we can tell that they're all being refracted at around the same index of refraction, which is causing them to go towards the same point here.
And these findings allow us to make the assumption that these are following Snell's law, and that is allowing us to determine where the image formation is occurring, which This, in the eyeball's case, would be where the retina is at. And this is where the image formation is occurring due to the light rays refracting once they hit the lens in the cornea. And the image formation then occurs here. And that is all for the presentation.